Thank you, Sarah and Sebastian, for having me, and welcome everybody to this anniversary talk. Today I want to talk about map apps or map applications in general, which you probably may know from apps like Google Maps or Google Earth, or also OpenStreetMap-based apps like Maps.me. And I want to explain on which concepts and techniques they are based and how they work internally. And for that, I divided this presentation primarily into 3 parts. In the first part, I want to give you a basic overview over the classic 2D map apps like Google Maps or OpenStreetMap-based apps like Maps.me, and on the underlying concepts. And in the second part, I want to go deeper into 3D map applications and also into current trends like HD maps, for example. And finally, I want to give you a short demonstration of how you could build your own map application or web map application based on a popular open source framework. But before we start, I want to introduce myself. My name is Markus Tremmel, and I work as a software engineer at a company called Rohde and Schwarz in Teisnach, which is located in the Bavarian forest. And there also my main work focus is on developing GIS and map applications. So primarily all the stuff I'm talking about today, I'm also working on. And if you want to do any further discussions after this talk, you can contact me at the following email address. If you need some help by developing GIS or map applications, then you can, don't hesitate to contact me. Okay, 15 years ago, in 2004, there happened something which changed the whole map industry. But not also the map industry, also our lives, or the way we navigate or locate or plan our journeys, for example. Because this was the time where the first version of Google Maps was released. And this was the moment where maps got mainstream. So everybody started to using them. And the interesting part about that map is when you look at the map from this time. So this map was even a better version, but it was primarily in the center of the map. There was the map view, and on the side there was some navigation bar or navigation widgets and something for finding businesses and so on. But the really innovative part about that map was the map view, because Google was one of the first map provider who provided a worldwide zoomable and panable map via web interface. So everybody could access it just with a web browser. And this was the innovative thing about that. And when I first saw that, I thought about how could it be possible that that Google can display the whole world only in a web browser or even on a mobile device. And the concept behind this is called raster tiles. So the point about that is that maps, we are talking about really large amount of data. So we're talking about multiple terabytes of data for the whole world, or even hundreds of terabytes, depending on the resolution of the maps. So you cannot stream the whole data at once from a server to a client, or to deploy it within an app. That isn't possible. So Google did the following thing. They used a concept called raster tiles. And with this concept, the whole map is divided into smaller pieces. Like you can see it here on the side of this slide. And you divide it into, the smaller pieces are called tiles. And every tile is, when we're talking about raster tile, is an image. Normally it's a PNG. And there's a second concept about that the map is tunable. You know that when you turn the mouse wheel and zoom in, and then another zoom level is loaded. And so you have also different zoom levels. Normally you have 19 in OSM and 21 normally in Google Maps. So starting by zoom level 0, the whole world is displayed in just one tile. So one PNG or one image. which normally has about 256 to 256 pixels. Or on high resolution, like retina displays, you have about 512 to 512 pixels. And then when you zoom in, then the map gets divided into higher resolution tiles. These tiles have again 256 pixels, for example, but you have something like a quadri data structure. So normally this tile is divided by 4. So in the next zoom level, in zoom level 1, you have 4 tiles, then 16, and then 64, and so on. So the more you zoom in, the more detailed the map gets, and the more a higher resolution you can achieve with that. And so yes, with the outermost zoom level, the entire world can be rendered in a single image. And as you can see it here in this illustration, if you look at the zoom levels, you see the tile explosion. You're starting at zoom level 0, 1 tile, then 4 tiles, then 16, and so on. And then at 20 or 19, you have millions or even billions tiles, a billion of tiles. And also a very interesting or important concept about that is, so depending on the zoom level, different types of information are displayed. So starting by zoom level 1, the whole world is displayed in just 1 tile. So there you can see the oceans and the landmass. But it makes no sense to display in the first zoom level also the roads or the buildings, for sure. That makes no sense. So the more you zoom in, the more detailed information you get. So at zoom level 5, there's displayed the landmass. At 10 cities, 15 streets, and then building 20, at zoom level 20, the buildings are displayed. And all these tiles are responsible for merging together all these tiles to a single map. You have something like a web mapping framework, which is responsible for, or let me say it in other words, the tiles are normally stored on something like a map server. And the web mapping framework is responsible for accessing or requesting the tiles from a map server and putting them together to a final map. And there are different numbering schemes how you can access these tiles. Normally you have, or it's a standard to do it via an HTTP GET request. And it's something like a very common standard is the XYZ standard. So you can access the whole tiles. I will show you this now in an OpenStreetMap demo. So this is the normal view where you start accessing the map or displaying the map. And I open now the Chrome developer tools, so we can see the network traffic which is transferred via HTTP from the server to the map client. And if we zoom in, there you can see now we are at zoom level 1, 4 tiles are displayed now, or are requested from the server and merged together to a final map. And we can open this in the browser also. We are typing it into the address bar. You can see this is now 1 of 4 tiles in the zoom level 1. So, and you can access this, like I said before, via a simple HTTP GET request. And the components of this are at the first point, or the first fragment of this URL is the zoom level, then the index in X direction, and then the index in Y direction. And again, if you zoom deeper into this map, then again more tiles are loaded in different zoom level. Now you can see here, this is zoom level 4. So, and then as you can see, the tiles are getting more and more detailed now. So that's primarily all how Google did it in early days, and all the major map providers like Apple or Microsoft did this in the early versions of their map clients. But then in 2011 there arrived WebGL in the browser. So with WebGL you could do hardware accelerated rendering on the GPU. Before that you draw that normally on an SVG or on canvas. But now you could draw your graphics, your vector graphics, on the GPU via WebGL. So WebGL are JavaScript bindings for OpenGL ES, and OpenGL is a subset of OpenGL. And so you could access via JavaScript the GPU and can render your maps on the GPU, which is faster by factors. So you cannot compare software rendering on the CPU to doing that on the GPU. And this had a massive impact on how on the map architecture, and also the concepts, how maps are served from a server to a client. So, and the difference now is with vector tiles, the content now, as you can see here, it are again tiles, but the content of the tile is not an raster data, so no in PNG. It are vector data. Maybe you know that from SVG. So it's a description of the vertices or of the geometries which should be drawn on the client. So it's something like a rendering rule for the client. And there are a lot of advantages now are possible when you're using vector tiles. So therefore all the major map providers like Apple or Google switch to vector tiles in their map clients. And so now you could do stuff like dynamic styling on the client side. For example, now you have a dark theme or a light theme which fits very well to your UI. And you also have a much better user experience because you have smooth zooming. And I will show you this in a demonstration in the browser. For example, if we compare now raster to vector maps. So this is now a raster map. As you can see, we cannot rotate the map, and the zoom levels, so the zoom is very hard. It's not that smooth. And then compared to that, I want to show you the current technology with vector maps. So now you can see you can rotate the map, and the cool thing about that is, for example, the labels are aligned, or the fonts. And also the zooming is much more fluent than compared with the raster tiles approach. And also another big advantage is the size, when we compare the size of raster tiles to the size of vector tiles. Because with raster tiles we have terabytes of data. For example, if you want to do it to render it until zoom level 18, we have approximately 50 terabytes of data. With vector tiles we can store now the whole world with only, for example, 15 gigabytes approximately. So this all fits on a USB stick. So and this also made possible that we have now offline capable maps. Everybody, or some of you may know this from Google Maps, because again Google Maps switched in 2013 from raster to vector tiles, so it's using this approach. And if you open a Google Maps app or your Google Maps app and go to offline maps, and then you can switch to that view, and there you could download your map data to your smartphone. This is still limited to 40 gigabytes, but I think it will get bigger and bigger over time. So for example, if you want to go hiking or something, before that you could download the maps, and then if you have no internet connection or just Edge, you could access it from your cache. So this was a big improvement in this area. Okay, so the previous slides was primarily about 2D maps and the underlying concepts. As you could see it on the left side, so this is the classic map we have at the moment, and which the map industry calls state-of-the-art. So this is a flat 2D map on which are drawn symbols or lines and colors and fonts and so on. But when we look at our world, we see that the world is 3D, and the 2D use case is not fitting for every 3D, or there are things which can be done much better with 3D maps, and there are a lot of use cases. And if we look at the map industry, for example, to the game industry, we can see what's possible, what realistic 3D environments can be drawn, and which, for example, which high-resolution terrains, which high-resolution buildings, and so on. So we can see what would be possible. And so the question is why we don't use such techniques and such concepts from the game industry and using or bringing it to the geospatial or map industry. And that's exactly what is happening now. So more and more map engine switch over to 3D visualization, because we now have more and more 3D content available. So for example, we get that content from LiDAR or digital photogrammetry, and with a combination of a virtual globe and with terrain data and also high resolution 3D models, we can see the world from a bird's eye view. So that's a different concept like the classic cartography, where we see a flat 2D map like I showed before. At this point we can see real simulations of the real environment. And for me, that's more than just a pretty picture. It's a new way to analyze data. For example, you can use it for city planning or fluid simulation, or also transmitter tower site planning. But the complex thing about, or the hard thing about 3D is especially the large amounts of data. So we have massive data sets in 3D. And so we need a technique how we, again, like in the 2D, how we can subdivide that data into smaller pieces. I will show you that in the next slide. And also a big challenge is the rendering, because it's not so easy like when you do a software rendering with 2D. Because now you have to access the GPU, and you have to use OpenGL, for example, that you can draw on the GPU, which is quite more complex than the 2D use case. And one very promising concept how we can stream large amounts of 3D data from a server to a client are 3D map tiles. So 3D tiles are an open specification, even an industry standard, I would call it, for streaming massive 3D geospatial data sets. And there happened something, or there happened exactly that what I said before. It was taken, or the concept of that was taken from the game or movie industry, because they have similar problems. And okay, about the features of what it makes so strong, or 3D tiles, why are they are so impactful. The foundation of 3D tiles are a spatial data structure. So compared to 2D data sets, we can have now a multi-dimensional data structure, like octrees, for example, if you know that. And the interesting part, or what makes 3D tiles so strong, is that you reduce the object's complexity when it contributes less to the scene. So, for example, when you look at, or this is a picture of 3D tiles. So now you have not only 2D, 2D tiles, so now they are extended to 3D, so which are now bounding boxes. And the concept or the idea behind this is, so when you're very near to the view, the object and the textures are displayed in a very high resolution, because then you see it you want to see it in the highest resolution. And when it's very far away, for example at this point, you show it with a very low resolution, because then it's something like blurred and you didn't get all the details, or you don't get all the details about that object. And an interesting, or 3D tiles are not, or 3D maps are not only interesting for visualization purposes, so they are also interesting for analysis. So you could do even more complex analysis. And one interesting analysis is the viewshed analysis. So viewshed means, or a viewshed is an area which you can see from a given observer. So you place that observer, so this is your viewpoint, and you can see all the areas which are available from this point. So you can, as you can see here, they're all visible areas are highlighted green. And that you can even do with more observers, like here. And you get also the area highlighted, which is visible from all 3 observers. And this is very impactful because it can be used for example, in site planning for transmitting towers, which is very important for 5G applications. Okay, I want to just mention shortly current trends within the map industry. And one trend is, which currently are rising in the automotive industry, is HD maps. So HD maps are compared to the maps you know from the apps, have a very high resolution. So we're talking about centimeter precision. And this is important because the maps made for autonomous driving are used by robots and not used by humans. So they have to be very, very precise. So we're talking about level centimeter precision. And this is also a really new field, and where a lot of innovations are coming into the map industry. But the basic for HD maps are also things like 3D tiles, so displaying large amounts of 3D data. And another trend which is rising now are augmented reality apps. You may notice that from Google Maps, because is now available in all iOS and Android devices. For example, if you go, or it's called Live View, and if you open your app and you go to the Live View tab, as you could see it here, then you switch to a camera view, and on top of the camera there are displayed navigation information. So, and the cool thing about that is it's much more easy to navigate with that. So because now you don't rely on a classic cartographic map, so now the information where to go or where you have to go are displayed within the current view. Yes, you can try out this. This is a really cool feature, and this will for sure have a lot of impact.
Is this only available where you have Street View?
No, I tried it at my home, so in Bodenmais, and normally it should be, yes, it's based on a visual positioning system, so normally it should, or primarily they want to rely on Street View data, yes. But I think they have a backup with GPS. But yes, one key concept or key idea behind that is that Google wants to capture even more Street View data, that they have a very good image material which they can be used for this augmented reality and for positioning. Okay, so now I want to go into a practical part. I want to show you how you could display your own 3D map applications or implement that and display dynamic data on top of that map. But first I want to give you an overview over current popular web mapping frameworks. And one popular framework, or as you can see here, this is a trend over 2 years, an NPM trend, so the JavaScript repository. And as you can see, the most popular framework is still Leaflet, which is now maybe or is older than 10 years now, or 7 years or something. But Leaflet is still relies on raster tiles, so it's not that complex, for example, like Mapbox.gl. So with Mapbox.gl, so this is my favorite, I would say, because with Mapbox.gl you could render vector tiles. And you have very fluent maps, and you could also extrude buildings with that. So you have a 2.5D view. And there's also, so Leaflet is more easy to use. That's why it was so popular. And there are another framework like OpenLayers, which exists since years. And this is more the GIS stuff, so it's more complicated to use, but you can do things like coordinate transformations or raster projections. But that stuff you don't need the most time if you just want to do a simple map. And that's one reason why Leaflet was so successful. These are primarily, so besides Cesium, these are all frameworks which rely on 2 or 2.5D. But you cannot do 3D with that. So for that, I want to show you Cesium, which is some kind of state-of-the-art rendering stack for 3D. And Cesium is a geospatial 3D mapping platform for creating virtual globes, which is open source, so it is on the Apache license. So you are free to use it, even in commercial applications. And Cesium relies completely on WebGL, so it does hardware accelerated rendering. And the cool thing about Cesium, it provides a 3D, 2D, and also a 2.5D view. And this all with an unified or a single API. And with Cesium, Cesium also pushed the 3D tiles concept, which I showed you before in the last slide. So you can easily integrate 3D tiles into Cesium and display all the cool 3D buildings and their raw data very easily. Okay, now I want to give you a short demonstration of how you could build your own map application or 3D map application based on Cesium. So the first thing we need in Cesium is a viewer. So the viewer is the easiest way to access Cesium. And the viewer gets the Cesium here, the Cesium container, which is the div where the map should be displayed. And if you instance this viewer, you have a lot of things available. You get an scene, for example, which is the base concept in Cesium, and you get an image provider for displaying textures on the 3D map, and you get also the functionality for zooming and panning and so on. So we instance that, and in the next step we say the viewer to fly to Innsbruck with a 5 seconds delay. So, and we open that and show that in the browser. So you see here this animation, and as you can see here, at the moment it's still flat, so there's no terrain and no 3D data. But what's still available, or what's yet available, is the virtual globe. Now it's got invisible, but if we now zoom out.
Is this what is called Columbus view if you tilt 2D maps?
Yes. I can show you that later. The Columbus view is if you tilt it to 2.5D. Yes. So this is the 3D view, but there's even a 2D view available.
You said it is open source, but is the map provider also free? I mean,
yeah, that's an interesting point, or an important point. Here you get per default as an image provider, you get Bing Maps, so it's not free. But you could use other map sources. If you host your own map server, then you could do it for free. Yeah, I know, that's not so easy. You get not so much so high resolution data. Normally you can have, for example, Landsat data. So if you're talking about raster data, these have a resolution up to 30 meters. So one tile has 30 meter ground resolution. So it's still very limited. Okay, then in the next step we want to add terrain to cesium. That we can easily do if we say to the viewer, so we access the scene, which got instanced by the viewer. So the scene got instanced by the viewer, and say use that world terrain provider. So now we are going to Cesium Ion, which is the online provider from Cesium. But in the next step, I will show you how we can provide our own terrain data. So if we do that and reload in the browser, okay, it was cached. We have to reload it. But now we should see the terrain data. Yes, as you can see here, the terrain is rendered. So now we are in Innsbruck, and the textures, so the images are projected as textures. So, and if we zoom out, so we can see now we have in that easy way, we have a very impressive 3D environment with textures and terrain. So with image data and terrain data. Okay, the textures are now loading a little bit slow. It's probably because of the internet connection, but normally it's extremely fluent. So you see with that easy steps, you could provide terrain and a simple image. And in the next step, I want to show you how you could provide 3D tiles, which I showed you before. So 3D tiles or buildings and terrain are separate things in Cesium. So the terrain you access via what's called a quantized mesh. So that's separately hosted by the map server. And 3D tiles are for displaying buildings and other 3D objects. And so we could do that with that command. So you create an Cesium tile set, which is referencing the 3D tiles on the server, which is referencing a JSON. And in this JSON, there is listed which 3D tiles are available. And this is the complicated part about Cesium. So it's not complicated to display that. As you can see, it are just 2 lines of code, but to create that 3D tiles. There is, at the moment, there is no free 3D tiles converter available. There are commercial ones, but it's not so, it's a little bit expensive to use them. But you can do it of your own, so you can create your own 3D tiles converter, but 3D tiles are a little bit or a complex format, so you have to invest some time for doing that. And again, when we switch, we are now using our local terrain. So we are created a local terrain. That's again is very easy. because that you can do with open source tool like Cesium Terrain Builder or Tin Terrain. So, and you get the map data, for example, from a mission called SRGM, which was a NASA mission. And there you get the terrain data for free. And you could take this terrain data and use that open source tool, and there you could create your own terrain tiles. And with that code, so with 2 lines of code, you could access your own terrain and don't rely on online map provider. Okay. And if we reload that, so now we can see we have the terrain and also simple buildings available. The buildings we generated there are from OpenStreetMap. So at some points there are generalized heights because not every OSM dataset has a height for a building. So these are called LOD1 buildings. So with LOD1 you have no roofs or something, or no windows or no detailed informations. But for the first impression it's not bad. And as you can see, it zooms very, very smoothly. Okay, and in the next step I want to show you how you could then visualize your own data on top of that map. So we now provided the base data, so in terrain and the buildings and the maps, and now we want to draw dynamic data. First of all, I will show you how you draw a static line, because that's the key concept. If you understand that, then you know primarily how Cesium works. Okay, so I now turn off the buildings. It's more easy to see that when no buildings are available. So what we do here, we use an API called Entity API. So with that you could easily add entities to Cesium. And an entity has properties. For example, if you have a street or want to draw a street, the name of the street or something, so this can be displayed with a pop-up then, and it has a geometry. And here we have a polyline geometry, which means this is a line with a lot of line segments. At this point it has only one segment. So here we have the starting point, and here we have the end point. And so these are WGS84 coordinates, which you get from example if you do a GPS measurement with your smartphone. So the first is the latitude. No, it's the longitude, and the second coordinate is the latitude. And that we have to convert in a coordinate format which is called ECEF, which means Earth-centered, Earth-fixed. So this is a coordinate format which Cesium needs. But you can do that easily by using Cesium, the Cesium utility function. And here we add then, we say the width of the line is 10 pixels. And the styles we are using a color, a special kind of gray for that. And we say it should have a glow effect. So, and if we reload that, yeah, as you can see here, it's very simple, but that's the basic concept about drawing things like GPS tracks or something on a map. So, and it's also clamped to terrain. That means it runs along the terrain. We did that with that property. So if you have terroir data, it will follow the terroir with that property. So, and then at the next step, I want to show you how you could visualize dynamic data with cesium. So it's quite the same. We have something like that function. Comment that out. And then, so here we have, again, we add an entity. But then the problem would be if we add it like before static to an array, we have something like a flickering in the map. So we have to use the cesium callback property, and this property is called every frame. So probably if you have 60 frames, so about every 60 milliseconds or something, and is evaluated or evaluates this array where the position are stored. And then we fetch, we need something. I have a position server on the back end, which just where the map client now can fetch the data from a server and get positions. So we are doing this with the new fetch API. So we're saying at this URL you get your positions, and we add the current positions or the current position to the drag position array. So now we have also to create that array first and call that function. So, and now you should see how the line is dynamically added to the yes, as you can see here. Now we have something like a GPS tracking, which is a very important use case probably in all map applications. So the server or the client requests the position data from the server and draws then with the entity API, draws the current position of the GPS track. And we could also add which is in cesium called a Billboard. So primarily an icon. So here again, you add an entity to the map client. Again, you say, take these positions. And now we say it's not a polyline, not a line. We want to draw an ellipse now, as you can see here at this point, with 25 meters of in the major axis and 25 pixels also in the minor axis. So it's a circle. And we also say clamp to the ground, so it should align to the terroir. And if we copy that, we call that function, create Billboard entity. And reload that. Yes, you can see now we draw a simple billboard on that, so a simple circle which can stand for the current position. For sure you could do much more complex stuff with cesium. But so these are the primary concepts behind cesium and how you could display data with cesium. Yes, that's it. Thank you, and if you have any questions, feel free to ask.